Hello guys, welcome to Yebo Physics on a Thursday afternoon. My name is Arnold. I hope I find you well. I'm going to be with you this afternoon solving questions from tutorial 9. We're going to be looking at questions that pertain to sound waves, superposition and standing waves. So I welcome you all to this tutorial session. I hope that it's going to be of benefit to your learning. Please feel free to join in and interact with me as we solve physics problems together. The purpose of the tutorials are to help us be confident in solving physics problems. And those who are joining on the YouTube channel, feel free to type your contributions on the chat box. If you're joining live on the Teams platform, you can unmute your mic and share with us your contribution. Okay, so we're starting on question 19. That is the questions that are on the PHYV model site, and these questions are also of benefit to those that are from the FVV 101 group. So these questions are also good for your practice because the concepts and the content is the same. So please follow through as we discuss some of the questions. So we have about 10 questions that we're going to solve. That is from question 19 to 28, and the rest of the questions will be solved in tomorrow's tutorial session. If you have missed any of the questions that may be of interest to you that have been worked out from question 1 to 18, please do refer to the previous videos that have been streamed on the YouTube channel. So that is it for the introduction. I would love to see an interaction or have an interaction with you as we solve these problems together. And I hope you are getting prepared for your final exams. Alright, so let's get started. We're going to start with question 19, which is already showing on the screen there. Question 19, and I'm going to read through. So question 19 reads, I'm just going to expand this. Question 19 reads, the velocity of sound in seawater is 1.53 times 10 to the power of 3 meters per second. Find the bulk modulus in newtons per square meter of seawater if its density is 1.03 times 10 to the power of 3 kgs per cubic meter. So this is question 19. I'm going to write down the given data, question 19. And what are we given? We're given that the velocity is 1.53 times 10 to the power of 3 meters per second. And the bulk modulus B is given by, oh, that's what we're looking for, right? And what else are we looking for? What else are we given? The density, which is equals to 1.03 times 10 to the power of 3 kgs per cubic meter. So everything is in SI units, so whatever we get there will be in newtons per square meter, which is the SI unit. What else we're supposed to do is to identify the equation, right? To identify the equation. So you should know by now that your velocity is equals to the square root of your bulk modulus over the density. so which becomes the equation that we're going to use, right? So to rearrange, remember we're solving for the bulk modulus, so we can square both sides. That will be v squared equals to the square root of b over rho, and we square that to remove the square root sign, so this becomes v squared equals to b over rho, which means the bulk modulus is equals to rho v squared. So from here, what we need to do is to substitute, now that we know that b is equals to rho v squared. Rho is 1.03 times 10 to the power of 3, and our speed is 1.53 times 10 to the power of 3. And we should remember to square that. So what remains is for us to punch that. Okay, so I'm going to punch, this is 1.03. So we're now substituting, remember to square that, so we get 2.41 times 10 to the power of 9. Everything was in SI units, so this should be in that form. And do we have anything close to that? Let's check our answers. Yes, should be that 2.41. So indeed, that is what we are expecting to get. So I think we can proceed and move on to question 20. Question 20. It reads, to decrease the intensity of the sound you are hearing from your speaker system by a factor of 36, you can reduce the amplitude by a factor of 12 and increase your distance from the speaker by a factor of 3, and so on and so on and so on. So there are a number of possibilities. So there are 5 options that we've been given, and our intention is to decrease the intensity of the sound, okay, by a factor of 36. Right, so what do we know about intensity? So our equation should link intensity, it should link amplitude, it should link the distance. Okay, so basically that is what and we are being told that we have got our initial intensity, which I'll call I1, and it's going to be reduced by a factor of 36 to give us a new intensity of I2, which means if we were to come up with a ratio, it means I1 over I2 is equals to 36, because we're told that the final intensity has to be reduced by a factor of 36. All right, so once we've done this now, we now have to find the relation between intensity and amplitude, intensity and the distance, right? So if you recall from waves, we've got our intensity being equals to half mu omega squared amplitude squared v. Sorry, that's not intensity, but that's power, sorry. And why am I starting with this instead of? So this will be one of the equations that we're going to need, and we should know that intensity is equals to power per unit area, which is equals to power over, so our area, if this is a sphere, we could say 4 pi r squared, or just pi r squared if it's just a circular distance. But anyway, the formula for the area will not matter because everything else is constant. The 4 and the pi are all constant, so it will not affect our ratio in any case. Right, and we've established that our power is this equation, right? So which means that our intensity is equals to half mu omega squared a squared v over 4 pi r squared. But everything else is constant besides the amplitude and the radius that has been mentioned, right? So we can choose to ignore this, ignore that, ignore this, which means that our intensity is directly proportional to the amplitude and inversely proportional to the square of the distance. So it's directly proportional to the square of the amplitude and inversely proportional to the square of the distance of separation. Okay, and then what can we do next now that we have such a relationship? So we can choose to express I1 and say I1 is equals to A1 squared over R1 squared. These are parameters for the initial intensity before it was reduced. Whereas I2 will be equals to the amplitude has changed. It's now A squared A2 over the new distance, which is R2 squared. Okay, then we come back to this relationship. Come back to that relationship. We were dividing I1 by I2 and equate to 36. That is what we now want to do. Okay, so our I1, it's A1 all squared over R1 squared all over A2 squared over R2 squared. You equate this to 36. If you simplify this by division, it will now be A1 squared R2 squared over A2 squared R1 squared. You equate this to 36. If you simplify this by applying the square root on both sides, it would mean that A1 R1, so R2 over A2 R1 is equals to 6. Okay, because we've taken the square root on both sides and it cancels out the square. So I would like to put conditions for I1, the initial intensity, and I would say let area 1 be equals to 4 and let R1 be equals to 2. Then I substitute, right, and simplify that equation. So I'm saying In place of A1, what do I put? A1, I'm saying it's 4, and R2, I don't know what that is. A2, I don't know what that is, but I know that R1 is 2. These are the conditions that I'm putting. Okay, so if you simplify, this becomes 2R2 over A2 equals to 6. And if you simplify this, it becomes, if you simplify, that becomes, divide by 2 both sides, that becomes R2 over A2 equals to, it's equals to 3, right? Yes, should be equals to. All right. 2R2. Okay, we can just solve it as it is. If we, yeah, we can just solve it as it is. Did I simplify this correctly? If you multiply by 2 both sides, yeah, 4. Okay. Yes, I think we've simplified it correctly. So what can we do there? I think the next thing would be to substitute, right? The next thing would be to substitute. That will be, if we simplify that, let me see if in case I missed something there. In case I missed something there. Just want to confirm. That will be, simplify that to 2, 2, 2, 2. So we have got 6 equals to 4 R2 over 2A2 times 2 both sides. If you multiply by 2 both sides, what do we obtain? If you multiply by 2 both sides, go by 2 by 2. This becomes 12 equals to 4R2 over A2. And divide by 4 on both sides. I hope this is okay. Divided by 4 both sides, then 3 is equals to R2 over A2. Okay, so this becomes our simplified equation, right? We've just simplified the maths from here to there, right? Then all the way to simplify to find our equation that we can use to test all the possible solutions that we have. So we have R2 over A2 equals to 3. R2 over A2 equals to 3. So let's see if we've got any our amplitude. What is our amplitude? What is our amplitude? Our R is 3 over 12. That cannot give us 3. increase the distance, that's 3 over 4, and this one is 3 over 2, and your distance from the speaker, it's 4 over 3, and this one is 12 over 3, that gives us 4. I don't seem to be getting any of those. I don't seem to be getting any of those answers. Let me see, probably there's somewhere where I'm missing it. Probably there's somewhere I'm missing it from here. Let me just double check. A1, let's see the maths here. That should be A1 squared times R2 squared over A2 squared over R1. So I think, okay, that's A1 squared R2 squared over A2 squared R1 squared is equals to 36, and this becomes, okay, that's squared, right? So let me, we've already applied the square root, so this should be A1 R2 over A2 R1, which is equals to 6, the square root of that should give us 6. Then I'm saying let A1 be equals to 4, right? And let R1 be equals to 2, because what is happening to the amplitude, okay, hearing, reduce the amplitude, okay, anyway, so I'm just putting those conditions, so it becomes 4R1, sorry, R2, 4R2 over, what is A2? A2 we don't know, and R1 we said it's 2, so it becomes 2R1. It becomes 2R1, which is equals to 6. So it's equals to 6. If we've equated that to be equals to 6, then what remains is to simplify, right? It's to simplify. That becomes 2R2 over, wait, 2R2 over 2A2 over 2A2, that becomes that over A2, which is equals to 6, which is equals to 6. Comments, guys, in case I am losing it somewhere. Then I simplify that by saying R2 by A2 equals to, you divide both sides by 2, you should get 3. So it still remains R2 over A2. So the ratio of R2 to A2 should give us, the ratio of R2 to A2 should give us 3, according to what I have here. And what what does that simplify to be? What does that simplify to be? So it simplifies to be this, and now we have to look for a ratio for R2, which is the distance over the amplitude, which can give us a factor of 3. But I don't seem to see from our answers here any factor that can give us a 3 there. From our answers, what we have: increase your distance from the speaker by a factor of 3. Increase that. So for A, if we were to try A, it will be our distance, which is 3 over 12. B, that will be 3 over 4. C, that will be 3 over 2, and D will be 4 over 3, and E will be 12 over 3. And none of these are leading to the answer that we need. Could there be something wrong that I've done here, or something that I'm missing? Definitely there could be something that I'm missing on this part of the question, something that I may not be doing correctly. If you can identify that, please just flag it. Let me see if there are any comments. Please put comments, guys, in case I'm missing it somewhere. Alright, I don't see any comments yet. So our power is intensity is equals to power per unit area. Intensity is power per unit area, and intensity is directly proportional to the amplitude and inversely proportional to the radius. Yes, that we did. Alright, guys, probably there's something that I'm missing from this question. I'll skip this question and give it a second thought, then hopefully in tomorrow's tutorial it will be covered. I'll have to have a second look at it. This is question 20. I'll just bookmark this, and so for the sake of time, we'll just skip to question 21. We'll try out question 20 again tomorrow. I'll need to have a careful look at it. Which of the following does not have a precise definition in terms of the physical properties of sound waves? So we've got frequency, intensity, loudness, sound level. So which of the following does not have a precise definition in terms of physical properties? So in frequency, intensity, sound level, and wavelength, all these can be defined in terms of the physical properties of sound waves. So you have to recall the physical properties of sound waves, and you'll find that frequency, intensity, and sound level and wavelength are all or can be defined precisely by use of properties of a sound wave. So the only outlying answer is its loudness. Right, let's try out question 22. A clarinet behaves like a tube closed at one end. If its length is 1 meter and the velocity of sound is 344 meters per second, what is its fundamental frequency in hertz? What is its fundamental frequency? So what we should recall is that we need an equation for calculating frequency when the tube is closed on one end. The tube is closed on one end, so we should recall our equations for a tube closed on one end. F subscript n equals to nv over 4L. It would be 2L if it is closed on both ends. So basically that is, and for the fundamental frequency, this is the fundamental mode, so n is equals to 1. Okay, that's the fundamental mode. So which means this will be f1 substitute 1, and the speed is 344 over 4 times the length, which is 1 meter again. Okay, it's 1 again. So basically f1 is equals to 344 over 4. We need a calculator. over 4 should give us 86 hertz. 86 hertz. That's the frequency. We have an option there. So indeed, so what you needed to recall is the frequency when the tube is closed on one end. Now let's look at question 23. So we're given displacement xt equals to cos kx minus omega t. Its velocity can be obtained from, so we need to express our velocity in terms of the wave number k, right? I think we have looked at this concept in the previous topic, where we're looking at wave motion, right? Where we're looking at wave motion, and basically we are considering the speed to be equals to v is equals to omega over k, right? So we're expressing our velocity in terms of that, and v is equals to omega over k. is equals to omega k. I think that's a simple one. You just have to refer to your equations or to your notes where we looked at wave motion, right? Now let's jump on to question 24. Question 24, and what does it say? It says an organ pipe open at both ends. Okay, so this is question 24. So we've got a pipe open on both ends with a radius equals to 0.04 meters. What else? The length equals to 6.0 meters. What is the frequency in hertz? Frequency, oh, that's what we're looking for. And we're told that this is the third harmonic. Third harmonic. Assume its velocity v equals to 344 meters per second. So if it's the third harmonic, it means that our n is equals to 3. Okay. What is the frequency? Okay, so what we need is the equation for an open tube on both ends. So Fn is equals to Nv over 2L. And N is 3, so it becomes 344 over 2. What is our length? Our length is 6 meters. So we need our calculator. That's 2 by 6. Right, that's 86. And do we have that option? Yes, we do. Okay. Yes, we do have that option. So moving on, we can look at question 25. Question 25 reads, a straight string is observed to vibrate in 3 equal segments when driven by a 480 Hz oscillator. What is the fundamental frequency of vibration for this string? What is the fundamental frequency? Okay, so 3 equal segments. So I'm going to put a sketch. This is our antinode, which means n is equals to 3. Okay, so this is the length of our string from there to there, and this is L. Okay. So this is the situation that we're given, and we're expected to find the fundamental frequency. So now let's check from this equation. Let's check from this equation what would be the frequency. So we know that V is equals to F lambda, so frequency is equals to V over lambda. Frequency is equals to V over lambda. And our L is equals to, so we have 1,5 wavelengths up to this point. This is a complete wavelength, and this is half a wavelength. So we have got 3 lambda over 2, which means our wavelength is equals to 2L over 3. So our F is going to be equals to V over 2L over 3. So which means our F, our frequency, is equals to 3V over 2L. This is the frequency F3, right? That harmonic frequency. Now I just want to put up and see what is the condition for the fundamental mode. So for the fundamental mode, this is our length again, and we've got one antinode, which means n is equals to 1, and our frequency is equals to V over lambda, and in this case our L is equals to lambda over 2. As you can see that the length is half the wavelength, so which means our wavelength is equals to 2L. So which means our frequency is equals to 2L. So this is the first, or the fundamental mode. All right. So if you look at these two equations, okay, out of interest, let me do again for the case when we've got two loops until we generate a general equation. So this is our L, and we see for amplitude, it means n is equals to 2, and which means that our L is equals to the lambda. As you can see that we've got one complete wavelength from there to there. Okay, that's, so L is equals to 2, so which means for F2 this is equals to V over wavelength, right? All right. So if you look by inspection, if you look at all these three cases, we can come up with a general equation to say that Fn is equals to Nv over 2L, right? Where n is the nth harmonic, n is the nth harmonic. So for n is equals to 1, if you substitute 1 in place of n, this is what you come up with, right? For n is equals to 2, if you put a 2 there, this cancels that, you remain with this. For n is equals to 3, substitute 3, this is what you get. So if you look at the fundamental mode, our fundamental mode is V over 2L. Okay, so which means if you take your F3 is equals to 3V over 2L, and F1 equals to V over 2L. So in place of V over 2L, you can put F, and our F, yeah, you can put your F1, which is, so this becomes F3 is equals to 3. In place of that, you put F1. So which means the third harmonic is equals to 3 times the fundamental frequency. And in this case, we're looking for the fundamental frequency, right? And we're told that this F3 is 480 when we've got 3 segments, 3F1, which means your F1 becomes to 480 over 3. So F1 becomes, we have to punch that, 480 divided by 3, so it should be 160. And definitely we expect the fundamental frequency to be lower. Do we have 160? Yes, we can check that. So if you had to come up with a general equation, Fn is equals to 3F1, and I've tried to show where this relationship comes from, looking at different types of modes, starting with F1, F2, and F3. That was question what? That was question 25. So we can try out question 28. Oops, not 28, 27, 26 rather. Let's see, yes, 26. What does it say? What does it say? A string is stretched and fixed at both ends with a length of 200 centimeters apart if the density of the string is 0.015 gram per cubic per centimeter, and its tension is 600 newtons. What is the wavelength in centimeters of the first harmonic? Okay, so the length is 200 centimeters. Excuse me. So we can put a sketch. So this is our fundamental mode, like we did earlier. And we're told that the length is 200 centimeters. Okay. So we're also given density and the tension. And let's see, what are we being asked? We're being asked to find the wavelength of the first harmonic, which means the wavelength in this scenario that we already have shown there, right? That is 4, n is equals to 1. So we say this is half a wavelength, right? So the length is equals to wavelength over 2. So which means 2L is equals to the wavelength. So that's 2, and the length is 200 centimeters equals to lambda. So our lambda is equals to 400 centimeters. So this also follows the derivation that we did. If you want the general formula, it will be lambda n equals to 2L over n. And here we're considering for n is equals to 1. So our lambda at the fundamental is going to be 2L over 1. So which is still lambda equals to 2L, which is exactly the same with what we analyzed here. From there up to there, it's half a wavelength. It's half a wavelength. So which means that length is lambda over 2. Then you substitute and you still get your 400 centimeters. You'll still get 400 centimeters. Any questions? Let me see if there are any questions or comments. Okay, I don't see any questions here. I don't see any comments yet. Right, so if there are no questions or comments, we can proceed to question 27. Right, there we are. So it says a string with a fixed frequency vibrator at one end is undergoing resonance with 4 antinodes. Okay, with 4 antinodes when under tension T1. When the tension is slowly increased, the resonance condition disappears until tension T2 is reached. There being no resonances occurring between these two tensions, how many antinodes are there in this new resonance? All right, so let's put a sketch of the first scenario. 4 antinodes. 4 antinodes. So this is what first antinode. They should be equal. So it's fixed there as well. So antinode, 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 and n is equals to 4 at T1. Okay, at T1. at T1. So then what do we do next? Is to find the relationship. It is to find the relationship between tension and the number of antinodes, to see what happens when, is it a linear relationship? Is it an inverse relationship? So what do we know from what we have been, from the equation that we've been working on, which is this equation, because we're considering a string. We know that Fn is equals to 2L, F is equals to N V over 2L, okay? And the velocity V, this is another equation again, is equals to the square root of the tension over the density, mass density per unit length, right? So that is what we have. So we can simplify to then eventually check to see how tension relates with so if we were to change, this would be V squared T over mu. So we see a linear relationship between tension and velocity. Tension and velocity. So meaning to say, when tension increases, the velocity would also increase. Okay? When tension increases, the velocity would increase. So in this case, it says when the tension is slowly increased, right? So which means we are dealing with an increase in tension. So when tension increases, we expect the velocity to increase. Now let's see what will be the relationship between the velocity and the number of antinodes. So 2Lfn will be equals to NV, so this will be 2Lfn over N is equals to V. So which means that the velocity and the number of antinodes, when the speed increases, the number of antinodes should decrease. So the first relation that we're considering, this is the first relation that we're considering. One, we're told that the tension is going to increase, slowly increase until we match with tension T2, and at T2 we have a certain resonance that is occurring at that point, obviously with a different number of antinodes. So as we increase the tension, we are also increasing the speed or the velocity or the speed of the string, right? We're also increasing the speed, and by increasing the speed, we thereby reduce the number of antinodes. So which means we were at 4 antinodes, and we are told that in between from T2 to T1, there is no other resonance that is there. The resonance will occur when we reach the next node actually, which means so we're going to be reducing. This will die out, will die out, will die out, will die out until our pattern has got 3 antinodes. So this will be the pattern that is responsible for a tension that has been increased to T2, and the velocity has also increased. The velocity would have also increased. So, which means that our ans will be equals to 3 could be equals to 3 antinodes, because we're moving from 4 up to 3. Okay, let's check that. Alright, that is indeed what we are expecting to get. That is indeed what we're expecting to get. Then moving on to question 28, which is the last question anyway that we're going to be looking at today. The remainder of the questions will be tackled tomorrow. That will be the last tutorial that we have. Okay, I see there's a comment on the Teams platform there to say the linear density, so the 600 Newton and the linear density are not to be used for this question. That was question 26, right? Yes, question 26, yes, because the string is this, well, probably there could be another way of doing it, but that would be a longer way of solving for the problem. It says because it says the string is stretched and fixed at both ends. So we're just going back to question 26. It says the string is stretched at both ends, meaning it's like this, and it's like this. And if the density, if the density is that, and the wavelength is for the first harmonic, so the length of the string never changes, right? The length of the string never changes. So if it's tied like that, and if we are at a fundamental frequency, this is what we'll be having, and the length still remains as 200 centimeters. So probably, like I'm saying, there could be a longer way of solving that, and I think we would still get back to the same answer, where we can use the equation Fn equals to n over 2l square root of t over mu, and we can also use V is equals to square root of F, which is the tension, over mu, right? Okay, so if you are to solve that, I think we can still solve that using that method, but that would be a longer way. That'll be a longer way, but we can still do it just for the sake of clarity. So we can go back and still try that question out. It will still give us the same answer, or it should give us the same answer. So what we can do now, we know that for the fundamental mode, our this is going to be F1, which is equals to 1 over 2, I'm referring to this equation, that's 2 times the length, which is going to be 2 meters. We're going to convert back into SI units, right? deal with SI units, then we'll convert it back to centimeters. There's no equal there, times the square root of T, which is the tension, which is 600, over our density there has been given in gram per centimeter. So this is, so we can change that. That is 0.015 gram over centimeter. So we can multiply this by 1 kg over 1000 gram times 100 centimeters over 1 meter. So that it's in SI units. We can cancel out 2 zeros there, 2 zeros there, kg. Oh, sorry, kg is the one that is remaining. This gram is going, this gram is going, this centimeter is going, that is going. So we remain, our value is divided by 10. So that becomes 0.01015 kg per meter. So that's 0.0015. And we punch that. Right. So that is 1/4, right? We have 1/2 times the square root of 600 over, so we just went back to question 26 to try an alternative method using the tension and the linear density 0.0015. So we get our fundamental frequency being 158.1138. I'll leave it there, or 883 hertz. Right, now that we have that, because what we want is to eventually find the wavelength, we know that V is equals to F lambda, so the lambda is going to be equals to F will be equals to V over lambda. V over F rather, over F. So we realize that we don't have V, so we can now solve for V again using this equation that we had identified. So V is equals to the square root of tension over mu, which is equals to our tension is 600 over the mu is 0.0015. So let's punch that to find our mu. That's the square root of 600 over 0.0015. So oops, I put the wrong substitution. This should be frequency. Sorry. This is, I'm wondering why these are looking identical. It's frequency over mu. This is frequency over mu, and this is the frequency which we calculated is 158.11 158.1138. Okay, so I'm going to repeat that, so that becomes 158, the frequency that we got, 0.11388 over the mu 0.0015. We equate, oops, what have I done? Okay, that's 324. So the velocity is 324.668 meters per second. Now we can use our equation. Our lambda equals to 324.668 over the frequency, which we got is 158.113883. So we can say our ans divided by 158.113883. So we get our lambda being equals to 2 meters, and the 2 meters is equivalent to 200 centimeters. And for the fundamental mode, and our question here, what is it saying? So we got 2 meters approximately equals to 2 meters, which is that. What is the wavelength? So here we get 200 for the first harmonic. So it seems it's giving us two different answers. It's giving us a 200. It's giving us 200, and it's, so our lambda, if we do this, it's giving us 200 centimeters. And here, what do we have? Our length was, our length was 200 centimeters, 200 centimeters apart. So which one do we take now? Having, because our fundamental mode is like this, that, and we're told that the length is equals to and lambda is equals to 2L, which is what I had done earlier on. But now if you use this concept now of using equations, we're finding our L to be 400 centimeters actually, yeah. King James, would you want to respond to this one? What do you think, guys? We now have two different answers, should I say? So let me check again. So this is fn is equals to square root of t. Oh, we can check what the correct answer is, since we had not checked that. So earlier on we had got 400 centimeters, and so if the correct answer is 400. Is 400, which is what I had obtained earlier on using this simple analysis on question 26, where we're understanding that for the fundamental mode, it's half the wavelength. Fundamental mode, the length is equals to half the wavelength. So to get the wavelength, it will be 2L, 2 by 200. A string is stretched and fixed at both ends 200 centimeters apart, which means the length is 200 centimeters. So the wavelength should be equals to 400. And then we tried it out using these two equations. F is equals to n over that, and we got our frequency is 158, and we used our frequency to find the velocity. Use the frequency to find the velocity, and that is 158 over the density, which is 0.015. We got a velocity v of 324. And then say 324 by that, we get 2 meters as the wavelength, and we get 200 centimeters. And now this 200 centimeters that we get, wouldn't it then be 4? N equals to 2. So I'll leave it here, guys. I'll leave it here. So if we're using our linear density, it's showing us that we're getting 200 centimeters, unless there could be something misleading that I could have that I've done, but it's giving us 200 as the wavelength, and which is from the side, which is not the answer that we're expecting, and I was hoping that it would give us the same answer anyway, because we considered for the fundamental mode, for n is equals to 1, tension is 600. What is the wavelength in centimeter of the first harmonic? First harmonic, it's when it's for n is equals to 2, right? How many antinodes? So this, it should be the same. Okay, just a minute. This could be the same. Okay, so first harmonic has got one antinode. Second harmonic so because we're getting half of what we expect. We're getting half of what we expect to half of what we expect. First harmonic. Okay, I was just trying to look up on something there, but this is what I would give. I was still hoping that these should be the same anyway, but seems not so. Wavelength in centimeters of the first harmonic, because the first harmonic is the fundamental mode that is for n is equals to 1, right? So, alright, I'll also leave it here for you guys to brainstorm, and I'll also have to check why these are not giving us the same answer. I was expecting that they would give us the same answer. But thank you for popping up that question, making us realize the other side of the question. Right, the final and last question that we had. So we have to check if, we would have to really confirm why these are not giving us the same answer, why the first method and the second method are not giving us the first answer, are not giving us the same answer. Right, let's continue and look at the last question. I was just trying to see if I can see something quick that can help us. Alright, I was just responding to the comment on the chat. So let's see what we have on the last question. Which is 28, right? A very long string is tied to a rigid wall at one end while the other is stretched to a simple harmonic oscillator. Which of the following can be changed by changing the frequency? Which of the following can be changed by changing the frequency? I think we have F equals to NV over 2L, and we realize that V is equals to the square root of V is equals to the square root of what? I think I wrote this equation up here. I've gone too far. T over mu, and we see what changes the velocity is the tension. Alright, so it's definitely nothing to do with the speed. Changing the frequency will not affect, or will only affect the length, let me say. It will only affect the length. And remember, I said lambda n is equals to, we derived this expression and we put it there. Lambda n 2L over n, 2L over n, 2L over n. So which means if the L changes, the wavelength is also affected. So certainly frequency influences the wavelength. Frequency influences the wavelength. So it's only the wavelength, not the speed, because the speed is affected by the tension. Neither can the frequency affect the tension. Definitely it's not all of the above, because we have excluded tension and the speed. It can also not be none of the above, because we see that the frequency can affect the length, consequently affecting the wavelength. So the correct answer there will be the wavelength. The correct answer there will be the wavelength. Will be the wavelength of the waves on the string. Yep. So, like I said, I'm going to end on question 29. Question 29, where Lucian will take it up to question 38. That will be tomorrow. So that is it, guys, for today. Takeaway from today's tutorial would be to review question 26, which I will also do, and question 20, which I will also review. On question 26, using two different methods, we're getting two separate answers. So that needs to be checked as well. And question 20, I'll have to look it up again to see if I can get the expected answers that are there. Otherwise, thank you for following today's tutorial. This is what I had intended to look at. You will catch up the next tutorial tomorrow, that is Friday. Otherwise, from me and everyone else in the studio, it's a goodbye. All the best as you are working on your test preparations.